First of all, let's go to the engineering toolbox. Nice little website here, very handy, very useful. Link is in the description. And let's look at the solubility of methane. Solubility of methane, you see that it's not very soluble in water. Even less soluble at higher temperatures, 80 degrees. But when you get down to 0 degrees, you're talking, 0.04 grams per kilogram of water. We're talking about solubility of these gases in water. Now take a look at carbon dioxide. Carbon dioxide is much more soluble in water. At 0 degrees, it looks like Celsius. At 0 degrees Celsius, which is freezing, the solubility of carbon dioxide is 3.5 grams per kilogram of water. And as the temperature goes up, it still remains fairly soluble. At 40 degrees C, which is about 104 degrees Fahrenheit. And you're talking at 104 degrees Fahrenheit, you've still got a solubility of 1 gram per frickin' kilogram of water, 1 gram of carbon dioxide per kilogram of water. So, where am I going with this? Whereas, okay, same 104, you're talking about 0.015 grams per kilogram of water for methane. Where am I going with this? I'm going to take a little leap here. I'm just going to say this. It's my personal belief that the Pacific blob, the blob that cooked the Pacific, that's according to this National Geographic piece here. It was a pretty kind of a bad event. It was complete with toxic algae blooms and everything else. Killed a lot of sea life. It's my opinion that the Pacific blob, what was called the ridiculously persistent ridge of high pressure that created this blob of hot water in the Pacific Ocean, was caused by atmospheric methane. We know that there was a large release of methane gas from the Arctic permafrost and what have you in the years prior to and around 2013, which is when this blob showed up. So the blob lasted between roughly 2013 and 2016, and it's just now subsided, followed by now. The blob was a ridiculously persistent ridge of high pressure. So what they had in California along the western coast of the United States was they had higher temperatures, less precipitation. It was drier and hotter. So this is what happens when methane is released. Methane has a molecular weight of 16.04 grams per mole. Air has a molecular weight of about 29 grams per mole. Carbon dioxide has a molecular weight of about 44.01 grams per mole. So there's two cycles. There's two parts of this to methane release. And this is the thing that confuses people. Oh, are we gonna boil to death? Is the Earth going to turn into Venus, or is it going to turn into an ice cube because of this runaway methane release going on in the Arctic? You want to see my previous vlog about the Armageddon line, where I talk about the runaway methane. Just Google, do an internet search for runaway methane, and there's been a lot of discussion about this. Some they call it the clathrate gun, where they think there's going to be the extinction of mankind because of this. Which, who knows? You know what I mean? There are great minds out there at work on this, but not everybody is down with that whole scenario. So there's two schools of thought. with the methane, these large runaway methane releases, because methane is a greenhouse gas. The more greenhouse gas you release, the hotter it gets, the more methane gas is released, and it's a feedback loop that causes more methane to be released. Well, their thinking is that, that the Earth's global temperatures, global sea surface temperatures will rise by 10 degrees, and when it does that, it's basically game over. And some people are saying that the ocean might become anaerobic, and oceans might become anaerobic, in which case, that humanity and all life on Earth will basically, 95% of all life on Earth will disappear. There's an event called the Great Dying, which I believe was the Permian, somewhere around the Permian period or something like that. Well, there was also back then that temperature rise took 50 million years to take place. I'll have to look at it. It took a long time, and there was a lot of stuff going on. There was a lot of volcanic activity. You had Pangea. There was only one continent on Earth, Pangea, and it was breaking apart. There was a lot of volcanic activity around that. So there's just a lot of reasons why we could have had a mass extinction. But their thinking is that this cat right here, human extinction within 10 years. That's his name, Guy McPherson. Abrupt climate change and YouTube and so forth and so on. So the two schools of thought is, A, we either boil to death, which is what he's saying, that the temperature, sea surface temperatures are going to rise, and basically this is going to cause a mass extinction. It's a runaway cycle. It can't be stopped. There's nothing we can do about it, which is all probably true. And then there's another school of thought, which is the kind of sort of the school of thought that I'm kind of sort of in, is the sudden ice age. Let's say it's a new ice age. Oh, this is a new ice age movie? Oh, well, it's probably a cartoon. Let's say sudden ice age. Let's call it a sudden ice age. Sudden climate change ice age. There you go. This is the other side of the coin. Well, of course, this has to do with the grand solar minimum, which is supposedly upon us, and all of this kind of stuff. Okay. It's more complicated than that. To me, and it confuses people. There's two parts to this. There's two cycles. There's an up cycle. The methane cycle is an up cycle where you have methane with this light molecular weight, which is about the same as water. It's about 18.1 grams per mole. And 16.04 grams per mole. So water's a little bit heavier. So water, the most abundant greenhouse gas is water vapor. So methane, when it's released from the permafrost or what have you, it makes a beeline for the stratosphere. It goes up very high, and of course you have circulation. It gets moved around the atmosphere. It's a lot, it's a lot involved, but I wouldn't look for too much of it to become dissolved in water droplets of clouds or water vapor or anything like that. Furthermore, because of its low solubility, my point is that methane actually would inhibit nucleation of cloud droplets. In essence, the higher concentrations of methane would ultimately displace water vapor in the atmosphere. Now, methane is still a greenhouse gas. Water vapor is a greenhouse gas. But what this does is it causes the atmosphere to become drier and hotter. So when you have a mass methane release, what you have is a period where that plume of methane travels probably towards the equator because there's the gravitational pull is less at the equator because of the spin of the Earth. But essentially what you end up with is a plume of methane that comes down a bit like the Pacific blob. So you have a period of a number of years where the conditions are very hot and dry and not a lot of air movement. That's the displacement of the water vapors that have a super persistent ridge of high pressure. And so my contention is that the Pacific blob was caused by methane release. So this is a picture of what's to come. So the half-life of methane is, I forget, 8 or 9 years, something like that. Supposedly 8 or 9 years. Well, that's taking into account the concentration of methane is a low concentration of methane. Now, when we're talking about large releases of methane, the concentration of methane is much higher. So the higher that concentration you have of methane, the quicker, my belief, is that it's going to burn off. And the reason for that is because as it goes up and it makes a pocket, and there's, you have a higher concentration of methane in the upper atmosphere, ozone is produced from a catalyst, which is usually a volatile organic compound, and principally the big volatile organic compound is methane. In fact, so much so that you have to basically state they have something referred to as volatile organic compounds react in the atmosphere in the presence of sunlight. NOx, CO, and VOCs are called ozone precursors, motor vehicle exhaust, blah, blah, blah. Okay, so here you go down here, and methane is so much the common VOC that you have to have a term called non-methane VOC. NMVOC is often used to basically say that the VOC you're talking about is not methane. So methane is the most common VOC. And the methane is what's called a reaction body in the atmosphere. And what you have is it's a catalyst, and it's a catalyst that produces ozone. Ozone in turn turns around and eats up the methane, turning it into CO2. So you have a high concentration of methane to begin with. Hot, high pressure, dry, low wind conditions, indicative of of what you would have with a methane release. With that high concentration of methane, then you have massive amounts of ozone are released because you have a higher level of this. You have a higher level of catalyst in the atmosphere. More ozone is created, and along with other intermediate species. So when you end up with a higher concentration of these intermediate species of ozone and what have you. So the period of time that large quantity of methane is actually in the atmosphere is less than the 8 or 9 years or whatever the fuck it is that they claim that it is. So it ends up being less than that because you have higher concentrations, and it just looks like the conversion of methane to CO2, it's an exponential curve. So this large quantity of methane is released, but now at the same time, so there's your release of methane, but then it's the same kind of curve when you're talking about methane as a catalyst you have this conversion of ozone, and then because you have higher quantities of ozone, then you have this same exponential function in terms of how quickly the methane is eaten up by that ozone. So what you have is a slow period, a long period where you have the hot, dry conditions, and then the methane is rapidly, as this ozone builds up and builds up and builds up, then you have this critical point where the methane is basically being eaten up very rapidly. So then you have a sudden quick change from methane to carbon dioxide. Now you have a presence of, you have carbon dioxide falling out of the sky from the higher altitudes at 44.01 grams per mole. It's dropping like a rock past the 29 grams per mole, which of course, at those higher altitudes, you have less pressure and it's less dense. So, I mean, this is a sketch here. This is not the concentration that you're going to have at 30,000 feet, but it just gives you an idea of what the concentrations are like. The density might be like. Density, of course, is not necessarily a function of the molar mass. That has to do. There's other, like water, for example. The density of water is, liquid water is much different than water vapor, so you have electric forces, water is a polar molecule, carbon dioxide is not polar. However, this is just my belief that, you see that methane is a carbon surrounded by 4 hydrogens in a tetrahedral configuration, whereas carbon dioxide, you have the 2 oxygens on either side. And of course, water is a polar solvent, but when it comes into contact with carbon dioxide actually causes a hydrogen to be released multiple times. There's a process where carbolic acid causes hydrogen to be released in the water in several different processes. I don't really have time to look it up because I want to get to this main thread of an idea here. So here's the deal. Methane, there's the 2 different cycles that you have. The up cycle, the methane is released. It makes a beeline for the stratosphere. Then you have the hot, high weather conditions associated with that greenhouse gas effect, and the fact that the methane is pushing the water vapor aside. It's displacing water vapor because it doesn't like water. It has to do with the what kind of molecule it is. Then you go through a period of time with the sunlight and the other the other constituents of the atmosphere, the water vapor and stuff like that. Carbon dioxide is formulated, but the carbon dioxide is different. The carbon dioxide likes water, and so it gathers that water together, and the water droplets have a tendency to want to form around CO2, and it's a more acidic type of thing. And not only that, but it's heavier, so it's dropping now. It's cold, and it pulls that down. And so what the hot, dry conditions of the methane are followed by cold and wet, and stormy and high wind conditions, turbulence. And this is what we saw with the Pacific Blob phenomenon. The Pacific Blobanon, the Pacific Blob phenomenon, you saw the hot, high conditions followed by, just recently, this past winter, very wet conditions, flood conditions, high wind conditions, and I believe they said the tunnel tree in it's the big-ass sequoia or something. Big-ass tree was toppled, the one it's like it got a tunnel going through it over here somewhere in California. Don't know where it is, I don't know that much about California. But anyway, they had high wind conditions in the Sierras and so forth, like 100 mile-an-hour winds, like basically Category 4 the hurricane strength winds blowing and a lot of rain and things like that. This is associated, to me, it's indicative of the CO2 or the down cycle, where the CO2 is now making a beeline for the ground. It's pulling all that upper level coolness with it. It's sucking in the moisture. It wants to draw on that moisture, and it's cold and wet and high wind conditions. So this to me is the shades of the future, where you have methane released, hot, high pressure conditions like the blob, followed by cold, wet, stormy, high wind, flood conditions. It's a cycle. It's sinusoidal, if you will. So what the methane does is it causes the amplitude of your wave to winter, summer, winter, summer. So this is the kind of thing that we're going to be looking at. We're going to be looking at methane, carbon dioxide, methane, like this. And regionally, you're going to have higher concentrations of methane in the stratosphere and the upper atmosphere at certain locations, probably near the equator, than in other areas. And so it's very complicated. The reason that there's not a big consensus about human extinction is because there are reverse feedback loop. The methane feedback loop is not the only feedback loop in play. The water vapor, there's a cold feedback loop. There's a feedback loop that causes a moderation of temperature in terms of as far as the water vapor is concerned, because water vapor, yes, is a greenhouse gas, but when you have higher concentrations of it in cloud formation and so forth and so on, then what you have is you cause sunlight to be reflected back into space. So that actually cools the surface of the Earth. So, and this is the whole thing with methane. Methane, because this is just my belief, that because methane displaces water vapor, methane causes the Earth's surface to heat up that much more. But then it's followed by those higher temperatures cause more water to evaporate, so you have higher concentrations of water vapor that build up in the atmosphere and then cause a cooling trend. So that, coupled with the fact that the change in density of the seawater because of the added fresh water from the melting ice in the ice caps, causes this thermohaline circulation to shut down, which causes the Gulf Stream to shut down. The North Atlantic current, which is this current right here. Anyway, that shuts down and basically Europe freezes, because this is what's called a barrier current. You can see my previous vlog, the Armageddon line, and there's another one before that, even further back. Yeah, magnetic field effects on ocean currents are frozen doom. It's a lot of things at play. But anyway, that's what we're looking at. So it's a mistake to try to pigeonhole these processes into one thing or the other. Okay, so it's not going to be either boiling death or frozen doom. It's a cyclical thing. It's a sinusoidal cyclical thing where you have a methane high pressure and dry, hot, high, and dry, and low, cold, and windy, and blustery and stormy for the carbon dioxide. These are the two things here, and eventually, I don't believe that the planet can turn into Venus because there's too much water, and the heat capacity of water is such that I just don't believe that it's possible. We just can't turn the planet into Venus. It can be done, but you would have to, in order to do that, we would have to have some much more dramatic things happening than a little bit of methane release. The other thing too is about methane. Methane hydrate is frickin' everywhere, man. It's I think this is the one here. Methane hydrates, that shows you where the various deposits are. Visit the page. Right. So Global Carbon Project, gas hydrates, and so forth and so on. And this shows you where. So you got that right. Global Carbon Project. It's at globalcarbonproject.org. News, methane hydrates, so forth and so on. Hey, this guy's got some burning methane hydrate in his hand. They call it clathrate, whatever. The hydrates in permafrost, so forth and so on. But anyway, these are all you can see all the different deposits here. Thickness and sediment. A lot of it's locked up in sediment, and it doesn't really dislodge very easily. Some of the clathrate or the methane hydrate deposits are in shelves that are near subduction zones. Like we got a bunch of massive ones near the subduction zones across the west coast of America, right here by Oregon and California and so forth. A good earthquake or event, mudslide or something like that could cause a massive shelf of methane to be released, and which tells me that as much methane hydrate as there is out there across the ocean depths and all these different areas, that we have had to have had massive methane. The Earth has had to have seen massive methane releases before in the past. Perhaps even during recorded history, that we just didn't have the instruments to be able to tell, that it didn't happen. Now, of course, you have the ice cores and things like that, and I guess I don't know what the accuracy of that stuff is. You really have to delve into how it is that they figure out, how they tabulate, exactly what gases were in the atmosphere when. But they look at sediment deposits and they look at ice cores and things like that, and how much CO2 is in the ice core, So, and you see the solubility of according to temperature of carbon dioxide. So it gets pretty well locked up. The colder you get, it just really, CO2. It just really gets locked up, like in the ice. So You can tell something by that, I guess, I assume. So, but this is, has to be something that happens occasionally, where we have a runaway methane cycle. And if it was able to ever turn the Earth into Venus, then it would have done it by now. I mean, it's just, it would have done it a long time ago. Which maybe they'll tell you that, well, that's the Permian period, the Great Dying, which is something that Guy McPherson likes to bring up quite a bit. The Great Dying. He's always talking about the Great Dying, So basically what I'm saying is it's going to be a rough ride. Any way you slice it. It's going to be a rough ride, and it's going to suck for a lot of people. It's probably going to suck for May, and it's hard to really predict who it's going to really suck for the worst. The word is that there 20 million people are going to starve to death. 4 famines mean 20 million may starve in the next 6 months. Wow, holy shit. In the next 6 months, February 16th, 2017. Wow. Romania or Florida risk dying from starvation within 6 months and 4 separate famines. UN. So, wow, And there's just more of that to come, and it's just going to be a wild ride. You're going to have hot, high pressure, dry conditions, fires, and things like that, followed by massive floods and wind and rain and storm, and it's just going to be, and God knows what's going to happen in terms of the earthquakes and things like that. So it's just going to be a wild ride any way you slice it, and where it stops, it will probably take a decade or two, but where it stops is probably going to be, if I had to guess, and opinions are like assholes. Everyone's got one, and it stinks. Nobody really knows at this point. There are a lot greater minds than mine at work on this. But my guess is that it's going to stop with, since we're looking at the grand solar minimum and all of this stuff, that where it's going to stop is with ice, lots and lots of ice. Anyway, that's it. My name is R. Crosby Lyles. I went on. I wanted to try to snap this off real quick. I've been meaning to talk about this for a while. I haven't really been able to get to it because I have to work for a living, and I have a Patreon. Somewhere out there, but any amount of help is appreciated. Share the video, drop us a like and a subscribe, and I'm out there. I don't even know why I do this stuff. I don't know. I feel like I'm neglecting something if I don't do it. It feels like walking death. If I don't make videos and I don't talk about these things that are on my mind, I just feel like I feel like a walking ghost or something. I just don't feel like I'm doing what I'm supposed to be doing. And I appreciate all the support of my friends and out there, and I love you guys, and thanks for the support. My name is R. Crosby Lyles, and this is News from the Can. Thanks for watching. Thanks very much.
News from the Can.